Hello, and welcome to Night Cosmos Sleep. Tonight, we will explore a fascinating mystery from the early universe, the possibility that some black holes may have appeared before the galaxies surrounding them. This is a story of enormous masses, distant light, and clues that modern telescopes are only beginning to reveal. Along this journey, we will look at observational data, small red objects in the distant universe, and scientific explanations being tested with great care. There is no need to rush toward an answer. Instead, allow your imagination to open gently as we explore the unexpected rhythms through which the universe may have organized itself and grown. Let us begin our journey into a realm where black holes, galaxies, and ancient light are telling their own story in a way we have never heard before. In the earliest days of the universe, everything was still young, newly formed, and not yet fully shaped. The light from the distant galaxies we see today has traveled for billions of years, carrying stories of the first dark centers. Within those stories, astronomers have recently begun to notice something surprising. Some black holes may have appeared earlier than the rest of the galaxies surrounding them, as though the heart had matured before the body had time to grow. In the familiar picture, a galaxy is usually seen as the place where a black hole grows. First, there must be gas. Then the gas gathers and forms stars. Massive stars reach the ends of their lives, collapse, and leave behind small black holes. Over immense periods of time, those smaller black holes consume more material, merge with other black holes, gradually increase in mass, and eventually become the enormous black holes found at the centers of galaxies. That story sounds reasonable because it follows an order that is easy to imagine. Matter comes first, then stars, and only later do massive black holes appear. But new observations are making that sequence feel less certain. In extremely distant regions, where light has traveled for more than 13 billion years before reaching us, scientists are beginning to find signs of black holes larger than expected. They do not always lie inside old, wide galaxies filled with stars, as we might normally imagine. Some appear to exist within galaxies that are still small and young, as though the center had already grown before the rest of the system had truly begun. To picture this more easily, imagine a neighborhood that has only just begun to be built. The houses are still scattered, the roads are unfinished, and many areas remain empty. Yet in the middle of that neighborhood stands an enormous building, heavy and fully active, as though it had been there for a very long time. Early black holes create a similar impression. The galaxy around one may still be young, with relatively few stars and no clearly developed structure, while the central object already carries an extraordinary amount of mass. What puzzles scientists is not only that such a black hole exists, but how it could have grown so quickly while everything around it was still in the earliest stages of formation. A black hole is a region where gravity is so strong that even light cannot escape. Because of this, we cannot see a black hole in the same way we see a star. Instead, we recognize it through what happens around it. When gas and dust are pulled close to a black hole, they heat up, glow, and move at very high speeds. Those signs allow us to understand that something extremely massive is quietly drawing material toward itself at the center. The difficulty is that black holes need time to grow. A black hole cannot simply appear in an instant and immediately become enormously massive. To grow, it must pull in material, but when matter falls inward too quickly, the region around the black hole becomes intensely bright, and that radiation can push some of the surrounding gas away. Put simply, the faster a black hole feeds, the more chaotic its own meal becomes. This is why the presence of an extremely massive black hole in a young universe is not an easy question to explain. One example that makes this puzzle clearer is QSO1. This is an extremely distant object, seen as it existed when the universe was only about 700 million years old. That number may sound large, but compared with the universe's present age of nearly 14 billion years, it still belongs to a very early period. What makes QSO1 remarkable is that the black hole at its center may have a mass around 50 million times that of the Sun. Finding such a massive object inside a young galaxy is like discovering a core that has advanced far ahead of everything surrounding it. There is no need to keep too many numbers in mind. The main idea is enough. This black hole appears far too massive for the time in which it existed. If it began as a small black hole left behind by the death of a star, then it must have grown at an astonishing rate. Otherwise, it may have begun with a much larger seed. And if that is true, the story of the first black holes is no longer as simple as a star dying and leaving a black hole behind. The James Webb Space Telescope has brought this question into sharper focus. Webb does more than photograph distant objects. It collects extremely ancient light that left its source when the universe was still very young. Within that data are small red objects that appear only as faint points. At first glance, they may not seem unusual, but when studied more carefully, some of those red points show signs of very powerful centers. They may contain black holes that are pulling in matter, growing, and affecting the surrounding gas. Not every red point is a black hole. Some may be small galaxies. Some may contain large amounts of dust. Others may be regions where stars are forming very densely. But if even some of them contain unusually massive black holes, the question becomes important enough on its own. In the early universe, did some black holes begin developing before their galaxies? This does not mean that every galaxy began with a black hole. The universe rarely follows only one path. In some places, stars may have come first. In others, gas may have collapsed and formed a massive black hole very early. Somewhere else, a black hole may have grown rapidly for a short period and then faded, like a powerful flame that briefly flares before becoming quiet again. These possibilities do not rule one another out. They may all have occurred, depending on where the universe provided more gas, stronger gravity, or other unusual conditions. The important point is not a certain conclusion that black holes always formed before galaxies. What matters is that our familiar sequence is being expanded. A galaxy may not always have existed first as a complete home before developing a central black hole. In some cases, the center may have appeared very early, while the surrounding gas and stars only gradually began arranging themselves into a galaxy. When we study these distant objects, we realize that the early universe was far more complex than we once imagined. Gas gathered, stars formed, black holes pulled in matter, and light traveled outward and changed along the way. Even the smallest points of light can carry important clues and raise questions far greater than their appearance would suggest. And this is what makes the subject so compelling. It does not make everything we once understood completely wrong. Instead, it gives those earlier ideas greater depth. Perhaps in the young universe, darkness and light did not appear in one simple order. In some places, a black hole may have existed very early, quietly occupying the center while the galaxy around it was still learning how to take shape. What remains after such a discovery is not a final answer, but one clear impression. The early universe may have been more diverse than we realized. A small red point may be more than a distant speck of light. It may be evidence of an ancient dark center. A stream of gas moving around something invisible may reveal how a black hole was growing, and a black hole appearing far earlier than expected may lead us to reconsider a question that once seemed simple. In the earliest days of the universe, what truly came first? Before the discovery of black holes appearing surprisingly early forced scientists to reconsider the story, the beginning of the universe was often described in a fairly simple and understandable sequence. At first, the universe was still very basic, containing only a small number of ingredients. There were no dense fields of stars, no planets, and none of the rich cosmic dust that would appear later. What existed in the greatest abundance was light gas, mainly hydrogen and helium, along with a form of matter that did not emit light, but exerted gravity, helping gather everything into denser regions. This non-luminous form of matter is commonly known as dark matter. The word dark does not mean mysterious in a supernatural sense. It simply means that dark matter does not produce light that telescopes can detect directly. We know it is present because its gravity affects gas, stars, and galaxies. It can be imagined as an invisible framework. That framework does not shine, but it gives ordinary matter places where it can gather. Because of this gravitational influence, gas in the universe did not remain evenly spread forever. It began collecting within denser regions. When enough gas gathered together, it was no longer only a thin, diffuse cloud. It began to compress. The denser regions pulled in more gas from their surroundings. As more material gathered, gravity became stronger. As gravity strengthened, it drew even more matter inward. This process unfolded very slowly, compared with a human lifetime. But within the history of the universe, it was the first step toward the birth of large structures. From these seemingly simple regions of gas, the first stars began to form. Those first stars were not completely like many of the stars familiar to us today. They were born from extremely primitive gas made almost entirely of hydrogen and helium. At that time, the universe contained very few heavy elements such as carbon, oxygen, and iron, or the materials that would later help form rocks, water, planets, and living bodies. Without those more complex ingredients, early gas cooled in a different way. Some of the first stars may have grown extremely massive, shining brightly, burning intensely, and living only briefly. The more massive a star is, the faster it generally consumes its fuel. It is like a flame that burns with extraordinary power from the beginning, but because it burns so strongly, it cannot last for very long. If the first stars were truly very massive, they may have lived for only a short time compared with the age of the universe. As the fuel inside them ran out, they could no longer resist their own gravity. Their cores collapsed. Some died in enormous explosions that scattered material into the surrounding space. Others may have left black holes behind. A black hole born from the death of an early star would not necessarily have been enormous. It may have been only a small seed, many times heavier than the Sun, but still tiny compared with the supermassive black holes found at the centers of mature galaxies. The term black hole seed can be understood simply as a starting point. It is like a seed that already possesses extremely strong gravity, but still requires more time, more material, and favorable conditions around it before it can grow into something much larger. From there, the familiar story continues in a fairly clear sequence. A small black hole lies within a region rich in gas. The gas is pulled toward it. Before disappearing into the black hole, that gas often becomes hot and begins to glow. This later allows human beings to detect signs of a black hole, even though the black hole itself does not shine like a star. Each time it draws in more matter, the black hole becomes slightly larger. If it encounters another black hole and merges with it, its mass can also increase. Little by little, over an immense span of time, a small black hole can become a larger one. In this traditional picture, galaxies and black holes develop almost together. A galaxy contains gas and stars. A black hole lies near its center and continues receiving matter from the surrounding environment. As the galaxy grows, its central region also becomes denser. The black hole gains more opportunities to draw in gas, encounter other black holes, and increase its mass. After hundreds of millions, or even billions of years, it may become a supermassive black hole, meaning a black hole with a mass millions or billions of times greater than that of the Sunday. The important point is that this story requires time. It is not a transformation that happens in an instant. A star needs time to form, live, and die. A small black hole needs time to consume additional matter. Galaxies need time to gather gas, form stars, collide, merge, and grow. In the familiar picture, supermassive black holes are therefore the result of a long process. They are like ancient cities built over many generations, rather than complete buildings that suddenly appear on empty ground. This is why new observations showing that some massive black holes were already present, very early, make the question much more difficult. If the universe was still young, if galaxies were only beginning to form, and if relatively few stars yet existed, where did these black holes find enough time to grow so quickly? Did they begin as small seeds and increase in mass at an extraordinary rate? Were they already much heavier than normal at the beginning? Or were there other paths of formation that the familiar story has not yet fully described? The usual account of cosmic development still makes a great deal of sense. Gas gathered. The first stars were born. Massive stars died. Small black holes appeared. Those black holes consumed more matter, merged, and gradually became the large central objects found in galaxies. This sequence helps human beings understand many features of the mature universe. But when we look toward the earliest period, where everything had to happen within a much shorter amount of time, gaps begin to appear in that sequence. The greatest gap concerns time. This is not because the older model is unreasonable, but because it requires a sufficiently long period of growth. The early universe, however, seems to have contained large black holes before that gradual process had enough time to unfold completely. This does not make the older story disappear. It simply suggests that it may not be the whole story. Alongside the slow path from stars to black holes, there may have been faster and rarer paths that occurred only under highly unusual conditions. The question of the first black holes now becomes clearer. If they appeared so early, how quickly did they grow while the universe was still young? The familiar story of stars and galaxies provides the foundation for understanding the problem, while new observations continue expanding the picture. It is here, along the boundary between what is known and what remains mysterious, that we begin to see why the growth rate of early black holes presents such a major challenge. Black holes, even though they are often seen as powerful dark centers, cannot grow without limit. The first difficulty comes from the way matter interacts with the black hole itself. When gas and dust fall toward the center, they do not disappear immediately. The region around the black hole becomes hot and bright, releasing energy into the surrounding space. That energy can actually slow the inward flow of matter, acting like a gentle but constant opposing force. This idea is commonly known as the Eddington limit. In simple terms, gravity pulls matter toward the black hole, while the energy produced by infalling material pushes some of that matter away. A black hole therefore cannot consume material too quickly without encountering resistance. This is why the accretion rate depends not only on how much matter is available, but also on the energy being generated around the black hole itself. If a black hole begins with a relatively small mass, only a few dozen or a few hundred times the mass of the Sun, growing into a black hole millions of times heavier than the Sun within a short period becomes an extremely demanding problem. It needs enough material, favorable conditions, and long periods of efficient accretion without major interruption. If the accretion process is repeatedly disrupted, the black hole will not have enough time to reach the mass revealed by observations. Scientists study the light surrounding black holes to understand this process. As gas circles a black hole, it produces light with distinctive features. From the speed of that gas and the brightness of the surrounding region, scientists can estimate how quickly the black hole is accreting matter. These observations suggest that some early black holes must have grown at very high rates to reach such large masses within a limited amount of time. This presents a major challenge because matter is not always abundant, and the energy released around the black hole continually resists the inward flow. One simple way to picture this is to imagine a volcanic opening drawing in gas from outside. If the gas arrives too quickly, heat and pressure from within begin pushing part of it away. A black hole behaves in a somewhat similar way. It tries to feed on matter. But the faster it feeds, the stronger the opposing force becomes. Its growth rate, therefore, does not simply increase in direct proportion to the amount of available gas. Another difficulty is that a black hole must grow through many different periods of accretion. Its growth does not follow a perfectly steady line. There may be bursts of rapid growth lasting several million years, separated by quieter periods when much less gas falls inward. Each of these phases affects the black hole's average growth rate. If the active periods are not powerful enough, or if the quiet periods last too long, the black hole may struggle to reach the mass seen in observations. These difficulties create a fascinating problem. The question is not only whether early black holes existed, but how they were able to overcome natural physical limits and grow so quickly. Some explanations suggest that early black holes may have begun with masses much larger than normal, perhaps forming from enormous clouds of gas that collapsed directly. Others suggest that black holes grew in repeated bursts, with short periods of extremely rapid accretion. Whatever path they followed, every explanation is trying to show how black holes could become massive within the limited time available in the early universe. It is important to remember that these limiting conditions are not identical in every case. One black hole may be surrounded by abundant gas and matter, while another may experience conditions that slow accretion, such as intense heating of the surrounding gas or the dispersal of material by the energy being released. Every black hole must find its own balance between gravitational pull and outward resistance, between the matter available and the matter pushed away. This balance determines the true growth rate of each black hole. This also explains why not every early black hole immediately became supermassive. Some may have grown enough to become the central black holes of galaxies, while still requiring much more time to reach their greatest masses. The most unusually massive black holes may have begun under especially favorable conditions, perhaps inside very dense gas clouds or through the direct collapse of gas, allowing them to experience faster periods of growth than more ordinary black holes. Astronomers rely on indirect observations to understand these growth rates. By measuring the movement of gas and dust around a black hole, they can estimate both its mass and the rate at which it is accreting matter. The early black holes discovered so far suggest that their accretion rates must have been extremely high, while still remaining within physical limits. This shows that even when black holes grow rapidly, they must still obey the fundamental laws of nature. In the end, the growth rate of black holes in the early universe is not a minor detail. It is one of the central reasons scientists are developing new ideas about how the first black holes formed and evolved. It is a problem of balance between gravity and resistance, between available matter and released energy, and between periods of rapid and slower accretion. These challenges make black holes powerful centers, but also objects constrained by natural limits during the earliest days of the universe. Understanding how black holes grew under these restrictions helps explain why some appeared earlier than expected and exceeded the predictions of traditional models. At the same time, it opens new questions about the physical processes that shaped the early universe. To understand why these early black holes have attracted so much attention, we need to look at how human beings observe them. A black hole does not reveal itself clearly like a star. Extremely distant galaxies do not appear as complete and detailed as nearby ones either. They often show up only as tiny, faint, red points of light, sometimes so similar that they are difficult to tell apart. For this reason, the important task is not only to see them, but to read the information carried within their light. The James Webb Space Telescope was designed to work especially well with the kind of light that reaches us from distant objects in the universe. That light no longer has exactly the same form it had when it first left its source. As it travels through expanding space, it becomes stretched. We can picture this simply as a cord being pulled longer. As the cord stretches, the distance between points along it also changes. With light, when its wavelength becomes longer, it shifts toward the red end of the spectrum and eventually into the infrared. Infrared is a form of light that the human eye cannot see directly. It lies beyond the red light familiar to our vision. Specialized telescopes, however, can detect it. This is why Webb is so important. Much of the light from the very early universe has traveled for more than 13 billion years and has been stretched into the infrared. If we observe the sky only with instruments unsuited to this kind of light, we could miss many important clues. This does not mean that Webb sees the past as though it were replaying a clear recording. The reality is far more difficult. Webb collects signals that are extremely weak and distant, and scientists must then analyze them carefully. A single point of light in the data may have several possible explanations. It may be a young galaxy. It may be a region where many stars are forming. It may also contain a black hole pulling matter toward its center. Looking only at the object's outward shape is not enough to distinguish among these possibilities. The light must therefore be separated and examined more closely. When white light passes through a prism, it spreads into many colors. Astronomers do something similar with the light arriving from distant objects. They divide it into different parts and search for particular signs within it. This allows them to learn what kinds of gas are present, whether that gas is hot or cold, how quickly it is moving, and whether a powerful source of energy may exist near the center. There is no need to remember the complicated name of the technique. The main idea is that light tells us more than whether an object is bright or dim. It also carries traces of the object's composition, motion, and energy. A narrow, bright feature in the data may reveal the presence of hydrogen gas. A small shift in the light may show that the gas is moving. An unusually bright region may suggest that something near the center is releasing a great amount of energy. This is especially important when studying black holes. Because a black hole itself does not emit light, human beings must observe the material around it. When gas is pulled close to a black hole, it becomes hot and begins to glow before disappearing from view. That light contains clues about how rapidly the gas is moving. If gas is traveling at very high speeds around a compact central region, it may be evidence that an enormous mass is hidden there. Webb allows these kinds of clues to be recorded in objects at extraordinary distances. This represents an important change. Scientists already knew that the early universe must have contained the first galaxies, but many of those objects were too faint to study clearly. Webb not only helps us see more of them, it also allows us to ask more specific questions. How many stars might this object contain? Is there a great deal of dust? How is its gas moving? Are there signs that a black hole is growing inside it? One idea worth understanding is that distant light does not mean only light arriving from far away in space. It is also light arriving from far back in time. Because light takes time to travel, when we observe an extremely distant object, we see it as it existed in the past. If its light took more than 13 billion years to reach us, then the image we receive shows the object as it was when the universe was still very young. This allows human beings to look back toward the universe's earliest periods, not through imagination, but through real signals. The farther we observe, however, the more careful we must be. A small red object does not automatically contain a massive black hole. Its red appearance may result from its great distance. Dust may also alter the color of its light. Strong brightness may come from stars or from hot gas surrounding a black hole. Every conclusion must therefore be tested against several different clues. Science in this case is not simply seeing a red point and calling it a black hole. It means reading the different layers of information in the light and gradually ruling out explanations that do not fit. That caution is part of what makes the new discoveries so significant. When several clues point toward a very massive center, when the light shows gas moving rapidly, and when the object is seen at an extremely early time, scientists begin to ask the question seriously. Could a massive black hole be hidden there? And if so, how did it grow? Webb does not provide the complete answer immediately. Instead, it gives human beings better data with which to ask more precise questions. In the past, we might have known only that a faint object existed at a great distance. Now we can begin asking what structure it has, whether its light comes mainly from stars or from heated gas, and whether an unusually powerful source of energy exists in its center. Each small answer helps clarify another part of the story of the first black holes. What is especially striking is that Webb's observations have not made the universe appear simpler. Instead, they reveal that the early universe contained more kinds of objects, more possible paths of development, and more cases that are difficult to fit into older models. Some objects are smaller than expected but contain powerful energy sources. Some galaxies are still young but show signs of extremely massive centers. Some faint red points may carry important information about how black holes and galaxies form together. Webb is therefore like a tool for reading the earliest pages of the universe again. It does not read them through words, but through light. Every infrared signal, every subtle change in color, and every sign of hot or rapidly moving gas may contain a line of information. From those lines, human beings are beginning to understand why early black holes are not merely unusual details, but important clues to the way the young universe built its first dark centers. As we move from the question of how quickly black holes could grow to the way Webb observes distant light, the problem becomes more concrete. An early black hole is no longer only an abstract idea that is difficult to imagine. It begins to appear through measurable signs: stretched light, gas moving around a central region, and intense energy emerging from a very small area. These are the clues that will lead us toward the small red objects found in Webb's data, where some of the largest questions about the first black holes are beginning to come more clearly into view. Among the data sent back by the James Webb Space Telescope is a particularly unusual class of objects, small red dots located at extraordinary distances in space. To the naked eye, or through older telescopes, they appear only as faint points. They are not brilliant, and they do not look as large as nearby galaxies. They show no majestic shapes, no sweeping spiral arms, and no bright fields of stars. Yet this modest appearance is exactly what makes them so interesting. The light they produce is not easily explained by the models scientists were once accustomed to using. Although these red dots are small, they may represent several different possibilities. Some may be extremely compact galaxies, containing relatively few stars, but large amounts of dense gas and dust. Others may be regions where stars are packed together very closely, with new stars continually forming, burning, and dying. Another possibility is that they contain black holes, accreting matter at their centers, quietly growing, without producing the same kind of light as the stars around them. This makes the red dots difficult to interpret, because every signal of light may be the result of several processes occurring at the same time. It is important to remember that a small red dot does not automatically prove that an enormous black hole exists inside it. The light we observe may be affected by cosmic dust, hot gas, or surrounding stars. Each point of light is only a clue, a sign that must be studied carefully before any conclusion can be made. Scientists use several methods to test explanations for these red dots. They examine the spectrum of the light to identify the gases present. They measure the speed of material moving around the object to estimate the gravitational force and mass at its center. They also apply energy models to determine whether an accreting black hole may be present. Only by combining several kinds of data can astronomers begin to understand the true nature of these red dots and imagine how an early black hole may have existed and developed in the young universe. What makes them so compelling is that sometimes a single tiny point of light is enough to make human beings pause and ask much larger questions about the universe. One small feature in an astronomical image may contain evidence of a massive center, a black hole quietly accreting matter, or a region of gas moving at extraordinary speeds. It reminds us that the early universe may not always have developed according to the sequence we once imagined. Stars first, black holes later, followed by the gradual growth of galaxies. These red dots suggest that many processes may have occurred simultaneously, in complex and sometimes unexpected ways. Each red dot is like a story in miniature. In some of them, enough matter may have been available for a black hole to grow rapidly. In others, the surrounding material may have been too sparse for the black hole to accrete very much. Scientists call these objects little red dots, not only because of their small appearance, but also because of the important meaning they may carry. Just a few tiny points of light could change the way human beings understand the history of cosmic formation. These red dots also demonstrate why observational data must be analyzed with great care. Their light does not tell the entire story. It provides only clues. By combining multiple layers of information, the light spectrum, the speed of the gas, and models of the object's energy, scientists can begin to picture the dark centers, the early black holes, and the ways they may have interacted with the galaxies around them. Another interesting point is that an object's physical nature does not always correspond to how large or bright it appears in an image. A very small red dot may contain a black hole millions of times more massive than the Sunday. By contrast, a larger-looking point of light may not contain such a powerful center. Understanding these objects therefore requires patience, detailed analysis, and careful comparison among many different kinds of data. The discoveries made by Webb through these distant red dots are opening a new view of the early universe. They do more than suggest that black holes may have appeared earlier than expected. They also indicate that the history of galaxy development may have followed more varied, branching, and complicated paths than traditional models describe. From only a collection of faint red points in the data, human beings have learned that the early universe was not simple, and that its first dark centers did not always develop according to the rhythm we once imagined. When these red dots are examined carefully, each object seems to carry a different combination of signs. Some light from burning stars, some light produced by hot gas, and perhaps a faint trace of a black hole accreting matter. Together, these signals create a picture that is difficult to interpret, yet deeply stimulating to the imagination. However small it may appear, each red dot has the potential to change the way human beings think about the formation of black holes and galaxies, opening new questions that the following chapters will gradually explore. The little red dots are therefore more than faint points of light in an image. They are small windows into the early universe, where the first dark centers may have been growing, where many complex processes were unfolding at once, and where one seemingly minor story may transform the way human beings understand the history of galaxy formation. When astronomers looked deep into the early universe, they discovered a remarkable object known as QSO1. The light we now receive from QSO1 began its journey when the universe was only about 700 million years old, an extremely short period compared with its present age of 13.8 billion years. This means that whatever existed at the center of QSO1 had to form and reach a significant mass within a very brief chapter of cosmic history. Observational data suggests that QSO1 may contain a black hole with a mass around 50 million times that of the Sunday. This is an enormous figure, especially when considered alongside the youth of its host galaxy. The galaxy had not yet formed many stars, and its structure was still in an early stage, yet its center already contained an immense concentration of mass. This creates a striking paradox. The black hole seems almost too large for the young home surrounding it. To obtain a clearer view of QSO1, astronomers take advantage of a phenomenon known as gravitational lensing. A galaxy cluster in the foreground acts like a natural telescope, bending and magnifying the light from QSO1, as though the universe itself had placed an enormous magnifying glass between us and the distant object. This effect makes it possible to observe extremely small details and different layers of light around the center. It allows scientists to study the movement of gas, the object's brightness, and signs of the black hole that would be much more difficult to detect in similarly distant objects without such magnification. QSO1 provides a vivid example of how massive black holes may have appeared inside young galaxies in the early universe, far earlier than the usual rhythm of development once imagined by scientists. It does not prove that all early black holes formed before their galaxies, but it makes that possibility serious enough to deserve careful consideration. The observations also reveal an important point. The mass of a black hole in an early galaxy depends not only on the amount of surrounding material, but also on the special conditions of its environment. Factors such as gas density, temperature, the rotation of the galaxy, and the efficiency of different periods of accretion can all influence how quickly the black hole grows. In QSO1, the central object appears to have reached a considerable mass even while the rest of the galaxy was still taking shape. The data show layers of gas moving rapidly around the center, becoming hot and producing light. These signs allow scientists to infer that a massive black hole lies at the center and is actively accreting matter. Every feature in the light and every movement of the surrounding gas provides valuable information about the black hole's rate of growth. What is especially remarkable is that although QSO1 is still extremely young, its central black hole is already massive enough to strongly influence the surrounding material. It pulls in gas, heats the environment, and may even affect how new stars form within the young galaxy. This shows that black holes in the early universe were not always small or weak. Some may have become dominant centers very early, helping establish their own rhythm of development within the galaxies that contain them. By studying QSO1, scientists have also learned more about how to analyze data from extremely distant objects. They do not observe the black hole directly. Instead, they study its effects on the surrounding gas, light, and matter. The black hole's mass is estimated from the speed of the gas orbiting the center, and from the energy signatures that the gas produces. This method applies not only to QSO1, but may also allow scientists to study many other early galaxies, in which massive black holes could have appeared surprisingly soon. The observations of QSO1 raise many unanswered questions. They force scientists to consider the possibility that the first black holes may have formed more quickly, grown larger, and become more powerful than traditional models once predicted. In this picture, early black holes were not merely quiet objects at galactic centers. They interacted with gas, stars, and surrounding matter, creating a more simultaneous and complex pattern of development than the orderly sequence we often imagine. The important point to remember is that QSO1 does not prove that every black hole formed before its galaxy. It simply brings one possibility into clearer view and opens a serious question. If black holes could appear so early and grow so rapidly, how did the universe's first dark centers form? These questions lead into the chapters that follow, where ideas involving black hole seeds, the direct collapse of gas clouds, and different mechanisms of growth will be explored. QSO1 has therefore become an important reference point in the study of the early universe. It is more than a distant object. It is evidence that black holes may have developed outside the usual rhythm once expected, encouraging scientists to reconsider how the first dark centers formed. Every layer of light, every movement of gas around the center, and every small detail recorded by Webb contributes to this unfolding story. QSO1 is not the final answer. It is a doorway into questions about accretion rates, central mass, and the interaction between black holes and young galaxies. It lays the foundation for understanding other black holes in the early universe and prepares us for further discoveries about the many different ways black holes may have formed. A black hole does not shine in the way a star does. It produces no light of its own from within and sends no visible glow into space. Because of this, human beings cannot observe a black hole directly. What we see instead is the gas, dust, and light produced by matter moving around the central region. This material forms an accretion disk where gas becomes hot, moves rapidly, and releases light before falling into the black hole. The speed of the gas around the center leaves traces in that light. When the gas moves rapidly, the spectral lines may become broader, shift in position, or appear distorted. Each of these features is a clue that the gas is being affected by the strong gravity of a hidden mass. These spectral lines allow scientists to measure the speed of the gas and then estimate the gravitational pull required to produce that motion. The basic principle is based on Keplerian motion. When gas follows an orbit around a massive center, its speed is related to the mass at that center. The closer the material is to the black hole, the faster it moves. By measuring the speed of gas at different distances, astronomers can estimate the mass of the black hole hidden within. One simple way to picture this is to watch flowing water. If a stone lies beneath the surface, the water may swirl around its position. The stone itself may not be visible, but the swirling current reveals that something is affecting the direction of the flow. Around a black hole, gas circling a massive center behaves in a similar way. Its motion reveals the hidden gravity and mass. This becomes especially important when scientists study extremely distant objects, such as early galaxies. The central black hole does not shine directly, but its influence on the surrounding gas and dust can be measured. By observing the light produced by the gas, scientists can estimate its rotational speed, temperature, and the mass of the central object. Every layer of gas and every small feature in the light carries valuable information about the black hole hidden inside. The analysis of light spectra is one of the main tools used in this work. When light from the gas reaches a telescope, it is separated into different wavelengths. Each wavelength carries part of the information about the composition and condition of the material. By studying the shifts and broadening of spectral lines, astronomers can determine the speed of the gas and then estimate the gravitational force acting upon it. When data from several regions are combined, the mass at the center can be calculated. This process is not simple because many other factors can interfere with the measurements. Gas motion may be affected by newly forming stars, winds from star-forming regions, or collisions between clouds of gas. To confirm that a black hole is truly present, scientists must compare several kinds of evidence at once: the speed of the gas, the brightness, the energy pattern, and the distribution of matter. When all of these signs agree, the case for a black hole becomes much stronger. Accretion disks do more than produce light. They also preserve signs of the rate at which matter is falling inward. As gas is pulled toward the black hole, it becomes hot and begins to glow. This light carries information about the energy being released and the rate of accretion. If gas is moving extremely fast around a compact central region, it suggests that the central mass is already very large. By combining these measurements, scientists can estimate the black hole's mass, determine how quickly it is growing, and evaluate its influence on the surrounding galaxy. These observations also help reveal the relationship between a black hole and its galaxy. A massive center can heat nearby gas, produce outward-flowing winds, and affect the way new stars form. This is evidence that a black hole is not simply a motionless object. It can take part in regulating the development of its galaxy, especially in the early universe when young systems of stars were still taking shape. The speed of the gas and the shapes of the spectral lines reveal not only the black hole's mass, but also the way it is accreting matter. A black hole does not grow at a perfectly steady rate. It may pass through periods of rapid growth separated by intervals of near silence. Studying the motion of the gas helps scientists determine the actual rhythm of accretion and estimate how much matter is falling into the black hole during each stage. This data also shows how astronomers solve a difficult problem, determining the mass of an object that cannot be observed directly. Instead of weighing it in a direct way, they study its effects on the material around it. Rapidly rotating gas, light from the accretion disk, and the distribution of matter all serve as clues. From these signs, scientists calculate the mass, the rate of accretion, and the influence the black hole has on its galaxy. Through this method, early black holes become less abstract. They begin to appear through physical signs, through light, and through the movement of gas. Observers can estimate their masses and growth rates, imagine how they interact with young galaxies, and ask how these dark centers formed during the earliest stages of the universe. When many objects are studied in this way, scientists find that black holes appear under a wide range of conditions. Their accretion rates differ, and their effects on their host galaxies are not always the same. The gas flowing around the center provides the information needed to identify the hidden mass, while also revealing the pace of growth and the impact on the surrounding environment. In this way, human beings can effectively weigh a black hole without ever seeing it directly. Streams of gas, features in the light, and signs of temperature together create the data needed to estimate the central mass. This forms the foundation for understanding how black holes accrete matter, grow, and influence star formation in early galaxies. These methods will lead us toward other examples in the distant universe, where faint light and moving gas continue to tell the story of the first black holes. Studying the streams of gas circling their centers is not limited to a single object. It provides a way to investigate an entire population of early black holes across the universe. The next discovery in the early universe leads us to GN-z11, one of the best-known distant galaxies. The light from this system began its journey when the universe was still very young, only a few 100 million years after the Big Bang. Data from the James Webb Space Telescope suggests that the center of the galaxy contains a black hole actively accreting matter, meaning that it not only exists, but is also strongly influencing the environment around it. The black hole's mass is estimated to be several million times the mass of the Sunday. Although this is smaller than the central black hole in QSO1, it is still remarkable because it appeared while the surrounding galaxy was still young. The central region was already powerful enough to affect nearby gas and matter, while also influencing the rate at which stars formed within the system. The observed signs include dense gas, strong radiation, and winds flowing outward from the center. The dense gas suggests that matter is being pulled inward and compressed around the black hole. Radiation from the heated gas affects the temperature and motion of the surrounding material. The outward winds, meaning matter being pushed away from the center, show that the black hole is highly active, drawing material inward, while also sending energy and matter back into the galaxy. These phenomena suggest that early black holes did more than simply appear at an unexpectedly early time. They could also play an active role. A growing black hole creates a powerful central source of energy, affecting the gas in the galaxy and the process of star formation. As matter falls inward, some of it is pushed back out, while the rest continues toward the center. This creates a rhythm of its own, in which black hole accretion and star formation occur at the same time and influence one another. The gas around the center moves rapidly, heats up, and begins to glow, producing energy that can be measured. This data allows scientists to estimate the central mass, the accretion rate, and the effect on young stars. It shows that a dark center in an early galaxy is not merely a passive object. It may take part in regulating the development of the system, changing the way gas behaves and stars form within the young galaxy. This observation broadens our understanding of the early universe. Earlier models often treated black holes as the later result of galaxy development, forming after stars had already appeared. GN-z11 suggests that a dark central object may form more quickly, interact directly with the surrounding matter, and strongly influence the process of star formation. The observations also indicate that not every early black hole was highly active. Some central black holes may have accreted matter slowly and remained relatively quiet, but the radiation and outward flowing winds seen in some galaxies show that certain black holes played an active role, helping regulate the pace at which their young host galaxies developed. These findings emphasize that a dark central object and its galaxy do not evolve independently. The interaction between the black hole and the surrounding gas creates an energetic system that can influence the rate of star formation, the density of matter, and the development of the galaxy's structure. Through GN-z11, human beings can see that the first black holes may not only have appeared early, but also had a significant impact. Gas moving around the center, rising temperatures, and emitted radiation all help clarify the rate of accretion and the black hole's influence on the galaxy. These observations allow astronomers to compare GN-z11 with other systems, estimate accretion rates and central masses, and study how black holes affect the overall development of young galaxies. The central black hole does not merely exist. It may help shape the rhythm of galactic growth, showing that the early universe was far more complex and diverse than earlier, simpler models suggested. In summary, this object expands the picture of early black holes. A central black hole may appear early, become highly active, and directly influence the gas and stars around it. This young galaxy suggests that a black hole may not be only the result of galactic development, but also an active participant in shaping that development. Information from this distant object provides an important foundation for understanding the many possible ways black holes formed and the central roles they may have played in the early universe. One possible origin for the first black holes begins with the earliest stars in the universe. When primordial gas gathered densely enough, stars began to form. These stars lived for a period of time, and then their inner cores collapsed when they could no longer produce enough energy to support the material above them. That collapsing core could create a small black hole. This is the most basic explanation, following a simple sequence: gas, then stars, then black holes. In the early universe, matter was not as chemically rich as it is today. There were no rocky planets, no cosmic dust filled with complex materials, and very few elements, such as carbon, oxygen, iron, or silicon. Those elements were created later inside generations of stars and released into space when the stars died. In the beginning, the universe was made mostly of the two lightest gases, hydrogen and helium. Hydrogen and helium are very simple ingredients. They were like the first building blocks from which the universe began constructing everything else. Clouds of these gases gathered within regions where gravity was strongest. When they became dense enough, the gas began to contract, the center grew hotter, and the first stars were formed. Scientists call these earliest stars population 3 stars. The name may sound technical, but its meaning is fairly simple. They were a very early generation of stars, born when the universe contained almost no heavy elements. Because the environment of star formation was different from what exists today, these first stars may also have been very different from the stars more familiar to us. One important point is that early gas could not cool as efficiently as gas in later galaxies. When gas has difficulty cooling, it often has to gather into a larger mass before it can form a star. Because of this, some of the first stars may have become extremely massive. They were not merely a little heavier than the Sunday. Some may have been many times more massive. The more massive a star is, the more intense the activity inside it becomes. It burns powerfully, shines brightly, and consumes its fuel quickly. We can imagine it as a large flame that rises very rapidly. That flame is brighter, hotter, and stronger, but it also does not last very long. If the first stars were truly enormous, they may have lived for much shorter periods than smaller and more stable stars. As the fuel inside a star begins to run out, the star can no longer maintain its balance. During most of its life, energy produced inside the star pushes outward, resisting the inward pull of gravity. These two forces keep the star stable. But when the energy source weakens, gravity begins to win, and the star's core collapses. If the remaining core is massive enough, it can become a black hole. This is the simplest path by which the first black holes may have appeared. Stars came first, and black holes came afterward. No highly unusual explanation is required. There is no need to begin with a dark center already in place. The first stars only needed to be massive enough, live quickly, die early, and leave the first black holes behind. These early black holes are often called black hole seeds. The word seed is easy to understand. A seed is not yet a large tree, but it may become one if it has good soil, water, light, and time. A black hole seed is similar. It is not yet a supermassive black hole, but it can become the starting point for one. A black hole seed, produced by one of the first stars, may have had a mass tens or hundreds of times greater than that of the Sunday. At first, this sounds enormous. Compared with Earth, the planets, or even the Sun, it is an extraordinary amount of mass. But in the story of supermassive black holes found at galactic centers, it is still relatively small. Those central black holes can contain millions or even billions of times the mass of the Sunday. The difference between a few dozen solar masses and several million solar masses is immense. If a black hole begins as a small seed, it needs a great amount of additional material in order to grow. It must pull in gas from its surroundings. It may need to merge with other black holes. It must remain inside an environment rich in matter. Most importantly, it needs time. Time is where the difficulty begins. In the mature universe, a black hole may have billions of years to increase its mass. It can grow slowly, one stage at a time, without needing to hurry. But the black holes observed in the very early universe did not have nearly as much time. If some had already reached millions of solar masses while the universe was still young, then their growth must have occurred much faster than usual. We can picture this as a young tree that has only just begun to grow. If it becomes a large tree after a long time, that seems natural. But if it reaches the height of an ancient tree after only a brief period, we have to ask what allowed it to grow so quickly. Was the soil unusually rich? Was it already larger than an ordinary seed at the beginning? Did it receive a constant supply of water? The same questions apply to black hole seeds. If the original seed was small, its growth had to be extraordinarily efficient. This does not mean that the path from the first stars to black hole seeds is incorrect. On the contrary, it remains a very important possibility. The earliest stars almost certainly played a role in producing some of the first black holes. When those stars died, they left behind small dark centers. Those centers could continue drawing in matter and become the foundations of much larger black holes later. The problem is that this path may not be enough to explain every case. For some early black holes, a small seed left by a first-generation star may provide a reasonable explanation. If the surrounding environment contained abundant gas, if the black hole accreted steadily, and if it encountered other black holes with which it could merge, it might gain a considerable amount of mass. But for the most massive black holes seen when the universe was still extremely young, this explanation begins to face serious pressure. A small seed must pass through a very long period of growth before becoming an enormous central object. It needs enough material, enough time, and favorable conditions. If even one of those is missing, it may not reach the mass indicated by observations. This is why scientists do not stop with the idea that the first stars simply died and left black holes behind. They also consider other possibilities. Perhaps some of the first black holes did not begin as small seeds. In certain unusual environments, the universe may have produced much heavier seeds from the start. A massive cloud of gas may have collapsed directly without first forming ordinary stars. Some black holes may also have passed through periods of extremely rapid growth before slowing down later. These possibilities do not remove the role of the first stars, they only expand the story. The main idea to keep is this: black hole seeds formed from the first stars represent the most natural and easily understood path. It begins with primordial gas, produces very massive stars, and ends when those stars collapse into black holes. But when this path is compared with massive black holes appearing very early, it seems more like one important piece than the entire picture. A small black hole must travel a long path before becoming an enormous one. It needs to draw in more gas, encounter more matter, and have enough time to increase its mass. But in the early universe, time was limited. This leads scientists to another possibility. Perhaps some black holes did not begin as small seeds. Perhaps they were born from enormous clouds of gas, when the entire cloud rushed inward so quickly that it created a much heavier black hole from the very beginning. In the early universe, not every cloud of gas broke apart to form many stars. Under certain special conditions, a large mass of gas could remain relatively uniform and collapse directly toward its center without fragmenting into smaller stars. When the entire cloud concentrated into one region, a massive black hole seed could form from the beginning. This is different from the path in which a black hole appears after the death of a star, where the central object begins as a much smaller seed. A black hole formed in this way could have a mass ranging from about 10,000 to 1 million times the mass of the Sunday. Because it begins with such a large mass, The central black hole does not need as much time to grow to tens of millions of solar masses. This is very different from a small seed left behind by a population 3 star, which would need a long period of accretion to become enormous. A heavy seed could influence the surrounding gas and matter almost immediately, while also strongly affecting the development of its young host galaxy. For this process to occur, several conditions must come together at the same time. The gas in the cloud must remain nearly primordial, made mostly of hydrogen and helium, with very few heavy elements. Heavy elements help gas cool quickly and fragment into smaller regions that form stars. Without many of those elements, the cloud is more likely to remain massive and continue collapsing toward the center. The movement of gas within the cloud also plays an important role. Sufficient pressure can prevent the gas from breaking apart and help keep the entire mass concentrated. Limited cooling prevents the cloud from losing heat too quickly, allowing it to remain intact while matter continues flowing inward. The surrounding environment must also provide the right amount of radiation enough to affect the cloud without destroying it, but not so intense that the gas is scattered away. When all of these conditions come together, a massive black hole seed may form at the center. This heavy central object does not remain passive. As it draws in gas, it heats the surrounding environment, produces radiation, and creates outward flowing winds. These processes affect the way gas gathers, regulate star formation, and influence the pace at which the galaxy develops. A black hole that begins with a large mass can become an active force from the start, directly shaping the growth of the galaxy around it. Observations rely on signs carried by the gas and the light it produces. The speed at which the gas rotates, its temperature, and the spectrum of its light can help scientists estimate the mass of the central object and its rate of accretion. When combined with other information, including gravitational lensing, these observations may allow astronomers to identify massive black hole seeds and evaluate their influence on young galaxies. These findings may also help explain the wide range of masses seen among early black holes. Some young galaxies contain unusually massive central objects, while others appear to have much lighter ones. Heavy seeds formed directly from collapsing gas clouds may have gained an early advantage, while smaller black holes produced by the first stars still had to grow gradually through accretion. The existence of several possible pathways makes the story of black hole and galaxy formation richer and more varied. It is important to remember that direct collapse was probably not common. It could occur only in unusual regions where the gas composition, pressure, cooling, and radiation were balanced in the right way. Not every early galaxy would have produced a massive black hole through this process, but the cases that did may expand our understanding of how quickly early black holes formed and how massive they could be at birth. Black holes created through direct collapse could also have a powerful effect on the galaxies around them. As they accreted gas, they heated the environment, released radiation, and drove winds outward. This changed the way gas gathered, influenced the formation of new stars, and regulated the galaxy's development. A central object that began with a large mass was not merely the result of galactic formation. It could also help direct that formation. From these ideas, scientists have come to recognize that early black holes may have followed several different paths. They may have formed from the deaths of the first stars, but they may also have been born directly from the collapse of enormous gas clouds, producing powerful central objects from the very beginning and immediately influencing the galaxies around them. This gives us a richer picture of how black holes may have appeared and developed in the early universe. They could form early, exert powerful effects, and take an active role in shaping their host galaxies. Every massive black hole seed is a clue that helps scientists better understand the variety of ways dark centers may have formed and the relationship between black holes and the matter surrounding them. There is one possibility that reaches back even earlier than the first stars. In this scenario, black holes were not born after massive stars died, nor did they form when enormous clouds of gas collapsed into dark centers. This possibility goes further. Some black holes may have appeared when the universe was still extremely young, before there were stars, before there were galaxies, and before the familiar structures human beings usually use to tell the story of the cosmos. These possible objects are known as primordial black holes. The idea may sound unfamiliar, but it can be understood simply. At a very early time, after the Big Bang during the young, hot beginning of the universe, when matter and energy had only recently formed and the universe consisted mainly of hydrogen and helium, some regions may have been far denser than their surroundings. Gravity could have caused those dense regions to collapse. If enough matter was compressed into a sufficiently small space, a black hole could form. What makes this type of black hole unusual is that it would not require a star to die first. It could form directly from differences in density in the early universe. This is the most important distinction. A black hole formed from a star requires gas to gather, a star to form, the star to live, and then the star to die. A black hole formed from a massive gas cloud still requires a dense cloud and special conditions that prevent it from forming stars first. But primordial black holes would have begun much earlier. They belong to a time before the first stars existed to collapse, and before there were galaxies capable of feeding dark centers. If primordial black holes truly existed within a suitable range of masses, they may have served as extremely early seeds. The earlier a seed appears, the more time it has to draw in additional matter. If one later entered a gas-rich region, as the first galaxies began to form, it might have grown into a much larger black hole. In this way, primordial black holes could help ease the problem of limited time, which is one of the greatest difficulties in explaining massive black holes that appeared surprisingly early. But this must be stated clearly. Primordial black holes are not a proven solution. They remain a hypothesis under investigation, not a confirmed conclusion. So far, there is no direct evidence showing that they were the source of the first supermassive black holes. The idea is appealing because it may explain some difficult observations, but an appealing explanation is not necessarily a correct one. Science must test this possibility in many different ways. If large numbers of primordial black holes once existed, they may have left detectable traces throughout the universe. They could have influenced the way matter gathered. They might have altered the motion of stars or gas in certain regions. They could also have produced unusual signals while passing through or interacting with their surroundings. If the expected evidence is not found, the range of possibilities allowed by the hypothesis must become more limited. One major question concerns their mass. If primordial black holes exist, they may not all be alike. Some could be extremely small, while others might be larger or much rarer. Not every kind would be capable of becoming a seed for a supermassive black hole. If they were too small, they might not have played an important role in forming galactic centers. If they were too rare, they could not explain the many massive black holes seen in the early universe. If they were too numerous, they might have produced signs that human beings should already have detected more clearly. The question, therefore, is not simply whether primordial black holes exist. A more useful question is, if they exist, how massive are they? How numerous are they? Where did they form? And did they enter the right environments to grow? A primordial black hole located in a region containing very little matter might remain small for an extremely long time. But one lying within a dense region of gas, just as the first cosmic structures were forming, might become a very early center of growth. We can picture this in a simple way. A seed falling onto bare stone will not grow into a large tree. But the same seed, placed in moist soil rich in nutrients and given enough time, may grow. A primordial black hole would be similar. Its existence alone would not be enough. The surrounding environment would determine whether it could develop into a massive central object. What makes this possibility so compelling is that it places black holes extremely early in cosmic history. If the idea is correct, black holes would not be only the products of stars. Some might be remnants of extreme conditions that existed soon after the Big Bang. They would resemble very ancient traces left behind from a time before the universe had taken on its familiar form. When the first galaxies began to emerge, some of these dark centers might already have been present, waiting within certain regions and ready to draw in more matter. However, this possibility should not be presented as more certain than it is. It does not mean that every massive black hole in the early universe came from a primordial black hole, nor does it eliminate the other possible pathways. The first stars could still have produced black hole seeds. Massive gas clouds could still have collapsed directly. Some black holes could still have grown through periods of extremely rapid accretion. Primordial black holes represent only another possible doorway, one that begins earlier and is more difficult to test. Because the idea is difficult to confirm, it must be discussed with caution. If clearer evidence is found in the future, primordial black holes could change the way human beings understand the early universe. Some black holes might then be viewed not only as the products of stars and galaxies, but as objects born during a much earlier period that later became the starting points for larger structures. For now, the most reasonable approach is to leave this possibility open. It is not the final answer, but neither should it be ignored. Primordial black holes broaden the question of how the first dark centers appeared. Black holes may have come from stars. They may have come from gas. And in a few unusual cases, they may have existed even before the first stars, as very early traces of the young universe. What is especially important is how this possibility forces human beings to think more carefully. If these dark seeds once existed, they might help explain how some black holes grew so quickly. But before a possibility can become reliable knowledge, science needs more evidence, more observations, and more rigorous tests. Until then, primordial black holes remain an open path, bold, scientifically serious, and important enough to remain part of the story of the first black holes. In the mature galaxies observed by human beings, the dark central object does not usually exist in isolation. The central black hole appears to have a close relationship with the stars around it. Studies show that the mass of a black hole often correlates with the mass of the surrounding stellar bulge, or with the speed at which stars move near the center. In other words, the more matter there is near the central region, the more massive the black hole tends to be, and vice versa. This relationship has led astronomers to an important idea. Black holes and galaxies may not grow independently. They appear to co-evolve, meaning that they develop together and influence one another over long periods of time. As a galaxy gathers more matter and forms more stars, its central black hole also receives additional gas and material, allowing it to increase in mass. This gradual process creates the stable relationship observed in the nearby universe. The idea of coevolution is further supported by observations, showing a connection between the speed of stars near the center and the mass of the black hole. When those stars move faster, the gravitational pull from the center is stronger, and the black hole is generally more massive. By contrast, galaxies containing fewer stars or less mass in their central regions often have lighter black holes. This data suggests that galaxies and black holes do not evolve separately, but continue to affect one another. However, early objects, such as QSO1 and other massive black holes found in young galaxies, raise a new question. In some cases, the central black hole had already reached a great mass, while the surrounding galaxy remained very small. This creates a problem. If the black hole was unusually massive from the beginning, did the relationship observed today also exist in the early universe? Or did the correlation between black hole mass and galaxy mass develop only after a much longer process? Data from the early universe suggests that there may have been a period when black holes grew ahead of the rest of their galaxies. During this stage, the mechanisms of coevolution may not yet have had enough time to become established. The gas around the black hole, the earliest populations of stars, and the energetic central regions had not yet developed sufficiently to create the balance observed today. This leads to an important conclusion. The The stable relationship between black holes and mature galaxies may not have existed from the beginning. It may instead be the accumulated result of development over time. This may also explain why some young galaxies contain black holes that are far too massive compared with the surrounding stars. When a black hole grows too quickly, it produces intense radiation and outward-flowing winds that affect the way gas gathers and stars form. This interaction may slow the galaxy's growth or regulate its development, allowing the stellar component to catch up with the black hole later. Over time, this process may gradually create the co-evolution and mass relationship observed in the nearby universe. It is important to remember that observations of the nearby universe show only the later, more stable state. They do not reveal the entire history of formation. The relationship between black holes and mature galaxies is the result of many factors. The black hole's accretion rate, the amount of surrounding gas, the rate of star formation, and the interaction between energetic central regions and the rest of the galaxy. In the early universe, these factors had not yet reached a stable balance, and massive black holes may have appeared before the surrounding stars had fully developed, temporarily disrupting the correlation. Theoretical models and simulations also support this possibility. When scientists simulate a galaxy beginning in its early stages, a black hole that starts too small needs a great deal of time to reach a mass that matches the surrounding stellar population. If the black hole grows too quickly, the rest of the galaxy must develop later in order to catch up, producing a slower process of coevolution. These simulations help explain why nearby galaxies appear balanced, while early observations reveal important exceptions. The relationship between black holes and galaxies can therefore be summarized in this way. It may not have existed in its present form from the beginning, but may have emerged through a long process. The black hole and the surrounding stars continually influence one another and interact with the available matter until a stable relationship develops, like the one observed today. When scientists look back toward early black holes, they see that co-evolution requires time to become established, and that many of the correlations observed today may be outcomes rather than starting conditions. The study of black holes and mature galaxies in the nearby universe reveals a close partnership between them. But observations of young galaxies, where the black hole is sometimes unusually massive compared with the stellar component, suggest that this relationship developed gradually. It may not have been present during the earliest stages of the universe, but formed over hundreds of millions of years as black holes and galaxies continued adjusting to one another. A star does not form simply because a galaxy contains a great deal of gas. The gas must be cold enough, dense enough, and given enough time to gather together. When a region of gas cools, the particles within it move more slowly. This makes it easier for them to draw closer together. The cloud gradually contracts, while the central region becomes denser and hotter. Only after a long process can a new star begin to form. If the gas is too hot, it cannot contract easily. If it is pushed too far away, it is no longer in the place where stars need to form. If it is constantly disturbed, clouds of gas have difficulty remaining stable. The environment within a galaxy is therefore extremely important. Having gas is one thing. Keeping that gas in the right condition for star formation is something else entirely. A central black hole can change those conditions. When a black hole pulls in matter, the surrounding gas does not fall into it immediately. The gas is drawn into rotation around the center, where it becomes hot and begins to glow. The region close to the black hole then becomes a powerful source of energy. That energy spreads outward, heating nearby gas, increasing its motion, or pushing it away from the central region. We can understand the basic idea simply. A galaxy needs cool, dense regions of gas in order to form stars. But a highly active black hole can make it difficult for the surrounding gas to remain in that state. It does not necessarily destroy the galaxy. Instead, it may make star formation more difficult, slower, or less regular than it was before. This is especially important in young galaxies. During their earliest stages, galaxies are still gathering gas and building their first generations of stars. If a powerful black hole is already active at the center, the surrounding gas may become heated too early. Some of it may be pushed outward. The rest may remain inside the galaxy, but no longer collapse easily enough to form stars. The galaxy can continue developing, but its rhythm of growth has changed. This may help explain why some early galaxies appear unbalanced. The black hole at the center is already massive, while the surrounding stellar population remains relatively small. This does not necessarily mean that the black hole has swallowed the entire galaxy. A more reasonable explanation is that the central object has altered the conditions of the gas. When gas cannot cool efficiently, stars form more slowly. When star formation slows, the galaxy needs more time to catch up with the mass already present at its center. Imagine a piece of land being prepared for planting. The soil is available and the seeds are ready, but there is a powerful source of heat in the middle of the field. That heat does not burn the entire area, but it dries the soil, strengthens the winds nearby, and makes it difficult for young plants to grow evenly. Trees may still appear over time, but their pattern of growth will be different. Some areas will develop slowly, others will remain sparse. Some may have to wait until conditions become gentler. A powerful black hole in a young galaxy can affect star-forming gas in a similar way. This effect is known as black hole feedback. Before using that term, we only need to understand the central idea. The black hole receives gas from the galaxy, and the energy produced around it then affects the galaxy in return. It is a two-way process. The galaxy feeds the black hole with gas. The black hole grows and releases energy, and that energy changes the gas that remains. When the black hole is only weakly active, this effect may be limited. The galaxy can continue forming stars relatively normally, but when the central region becomes highly active, nearby gas may be heated significantly. In some cases, gas can even be pushed outward in powerful flows. These are not winds in the ordinary sense, familiar on Earth. They are streams of matter, driven away by energy from the central region. As they move outward, they carry gas with them and reduce the amount of material available for star formation. The influence of a black hole is not the same in every galaxy. Some galaxies continue forming stars rapidly even with an active black hole at the center. In others, only the region close to the core is affected. Some galaxies experience a much clearer slowdown. The strength of the effect depends on how active the black hole is, how much gas the galaxy contains, and how energy from the center moves through the surrounding material. A black hole should therefore not be understood as something that only destroys. It is not simply an enemy of stars. In many cases, it acts more like a regulator of the galaxy's development. When the central activity is too strong, gas has difficulty becoming stars. When the activity weakens, the gas may cool again, gather together, and allow star formation to continue. A galaxy therefore does not grow along one smooth and steady path. It passes through periods of faster and slower development, with varying levels of activity. In the nearby universe, many mature galaxies appear to have reached some kind of balance between their central black holes and the stars surrounding them. But in the early universe, that balance may not yet have had enough time to form. If a black hole grew rapidly from the beginning, it could affect the gas before the galaxy had produced many stars. The central object would then move ahead, while the surrounding galaxy required more time to develop. Objects, such as QSO1, make this question even more important. If a black hole was already extremely massive inside a young galaxy, it may not only have grown rapidly, it may also have influenced the very environment that was feeding the galaxy. Gas serves as the raw material for both stars and black holes. When the central black hole takes in large amounts of gas and releases powerful energy, the remaining material can no longer develop according to its original rhythm. This may help explain why the relationship between black holes and galaxies in the early universe could differ from what we observe today. In mature galaxies, there is a relatively clear correlation between the central black hole and the surrounding stellar population, but that relationship may be the result of a long period of adjustment. In the beginning, the system may have been far more uneven. In some places, the black hole moved ahead. In others, the stars caught up later. Gas may have been heated or driven outward, slowing the rate of star formation. Seen in this way, the black hole is not the final result of galaxy formation. It is an active part of that process. It draws in gas, heats the gas, changes its movement, and sometimes slows the formation of stars. These effects do not necessarily stop the galaxy from growing, but they can cause it to develop according to a different rhythm. The main idea to remember is this: gas must be cold and dense enough to form stars. A highly active black hole can cause that gas to lose those necessary conditions. In some very young galaxies, the central black hole may therefore appear unusually massive compared with the surrounding stars, not because the galaxy is incapable of producing stars, but because the star-forming process was altered very early. A powerful center does not necessarily destroy its home, but it may cause that home to be built more slowly, to develop out of rhythm, and to require more time to become complete. In the early universe, even a shift in timing like this could create galaxies very different from the balanced systems human beings commonly observe in the nearby universe today. A massive black hole seed is not simply a dark object sitting motionless at the center of a galaxy. When it exists within a dense region of gas, it becomes a powerful gravitational center toward which surrounding matter tends to gather. Gas, dust, and other particles gradually begin circling the center, forming an accretion disk and helping build the central structure. In this sense, the black hole acts like the nucleus of the system, helping organize and concentrate the material around it. The presence of a black hole does not mean that star formation is completely prevented. As gas moves toward the center, it does not fall straight into the black hole. Instead, it circles around it, heats up, and begins to glow. Some of the gas may be pushed outward, while the rest remains within the galaxy, continuing to orbit and slowly contributing to the formation of new structures. In this way, the black hole both attracts matter and regulates the movement of the gas, while helping keep material concentrated near the center. A galaxy is not created by a black hole alone. It still requires dark matter, primordial gas, inflows from the wider universe, small mergers, the ability of gas to cool, and many other physical processes. The black hole serves only as a central anchor, a place where gravity is concentrated and where surrounding material can orbit and accumulate. With this anchor in place, matter can begin to form structure, gradually producing stars in the central region of the galaxy. As gas is drawn toward the black hole, friction within the accretion disk causes it to heat up and release energy. That energy affects the surrounding gas, changing its temperature, pressure, and motion. As a result, matter near the center is rearranged, creating its own rhythm in the formation of stars and the development of galactic structure. In mature galaxies, the relationship between the central black hole and the surrounding stellar region suggests a kind of balance. The black hole does not control everything, but its presence and its accretion of matter help regulate the overall pace of development, allowing the galaxy and its center to grow in a more coordinated way over time. In early galaxies, this mechanism may already be present, but it has not yet reached a stable state. A black hole that appears early can heat the gas, push it outward, or stir it up, slowing the formation of stars. The central region may develop more quickly, while the outer galaxy has not yet had time to catch up. Growth becomes uneven, and the distribution of stars and gas differs from what is seen in mature galaxies. A black hole, therefore, has a dual influence. It both concentrates matter and regulates the pace of development. When it is highly active, it heats the gas, disturbs it, and redirects its flow. When it is less active, gas can still gather and form stars. The black hole's influence is not simply destructive. It is more like an anchor that both holds matter in place and adjusts the rhythm of growth in the central region. This may help explain why, in many early galaxies, the central region develops more quickly than the outer areas while the galaxy as a whole continues to grow. A massive black hole seed may act as a coordinating center, shaping the rhythm through which matter becomes organized and stars begin to form. It can hold gas nearby while also heating it or pushing some of it away, creating a dynamic balance around the center. Observations suggest that the influence of black holes is not the same in every galaxy. In some systems, the black hole may only slightly adjust the development of gas and stars. In others, a more powerful central object may significantly slow star formation near the core. Although the strength of the effect varies, the black hole often acts as a coordinating center, helping the inner region form and develop according to a certain order rather than remaining completely chaotic. Heated gas, outward flowing winds, and energy spreading from the center all create an environment in which the galaxy develops differently than it would without a black hole. The central region is effectively anchored by strong gravity, while the outer parts of the galaxy grow more slowly, leading to differences in stellar density and structure. Seen in this way, a massive black hole seed becomes an important part of galactic development. It does not create the entire galaxy, but it helps define the center and regulates the way surrounding matter gathers. Under the black hole's influence, gas does not simply fall inward. It is organized, retained, and redirected, helping the galaxy develop in a more structured way over time. This way of describing the process makes the relationship between black holes and galaxies clearer. The black hole does not simply destroy or swallow all the gas. It attracts matter, heats it, gathers it, and changes the surrounding environment. Gas and stars form under the influence of the center, creating a coordinated rhythm of development within the galaxy. This is a dynamic balance in which the center helps regulate the system rather than completely controlling or destroying it. More broadly, this may explain why mature galaxies today show a balance between their central black holes and the surrounding stellar populations. In the early universe, that process had not yet been completed, and the central black hole may have developed first. But over time, the regulating influence of the black hole may have helped the galaxy move toward a more balanced state. The black hole therefore acts both as an anchor and as a coordinating center, making an important contribution to the formation and development of galactic structure. When we look into the early universe, one thing becomes clear. Galaxies did not all develop along the same path. There was no single formula for creating a galactic system. In some regions, the first stars appeared before black holes. When those enormous stars died, they produced black hole seeds. This is the familiar sequence many astronomers have often considered. Stars formed first, black holes appeared afterward, and then those black holes accreted matter and gradually increased in mass. In other regions, however, the process may have unfolded very differently. A massive cloud of gas may have avoided fragmenting into stars and instead collapsed directly toward its center, creating a heavy black hole seed from the beginning. Its large initial mass would have allowed the central object to develop more quickly, generate a powerful gravitational pull, influence the surrounding gas and stars, and regulate the formation of the young galaxy. Compared with the smaller seeds left behind by the first stars, this kind of black hole would already have had an early advantage in its development. In even more speculative explanations, primordial black holes may have formed from unusually dense regions of matter soon after the Big Bang, before any stars had time to appear. These dark centers would not have required material from a dying star. Instead, they would have formed from differences in density within the young universe. If they existed, they may have been the earliest seeds of larger black holes and could have influenced the development of galaxies from a very early stage. Beyond their different possible origins, the development of black holes and galaxies was shaped by many other factors, making each system unique. The gas surrounding a black hole, its rate of accretion, periods of merger with other black holes, the density of dark matter, the ability of gas to cool, and the surrounding radiation environment could all determine how an early galaxy developed. One system might contain a rapidly growing black hole, but form stars slowly, while another might form stars steadily as its black hole increased in mass more gradually. These factors created remarkable diversity in the early universe. The work of the James Webb Space Telescope is helping human beings see this diversity more clearly. Instead of observing only one or two galaxies, Webb's data allows scientists to study dozens or hundreds of early systems with different conditions involving gas, stars, black holes, and dark matter. Each observation is one piece of a larger puzzle, helping construct a more complete picture. The early universe did not always develop according to one steady rhythm. Each galactic system followed its own path, shaped by its particular conditions and surroundings. Seen in this way, black holes and galaxies did not necessarily have to develop at the same pace from the beginning. In some systems, a dark central object may have appeared first, influencing the gas and affecting the rate of star formation. In others, a smaller black hole seed may have formed after the first stars and then gradually accreted matter as the galaxy developed. These different possibilities do not contradict one another. Together, they may explain why astronomers observe galaxies and black holes with widely different masses, stellar densities, and structures, even when they existed during the same early period of cosmic history. This diversity also emphasizes an important idea. The early universe did not have to follow one universal formula. Galaxies could appear and develop through many different routes, depending on the gas, dark matter, background radiation, and initial distribution of matter. Black holes and galaxies continually interacted and adjusted to one another, but their rhythms of development and final outcomes could be very different. Webb is providing the detailed data needed to reveal this variety. By observing light from gas, stars, and dark central regions, scientists can see that every early galaxy represents a distinct case where the black hole, gas, and stars developed in their own way. No two systems were exactly alike, and no single formula can explain the entire early universe. More broadly, this encourages a more open scientific way of thinking. When considering the formation of black holes and galaxies, we should not expect one universal answer to the question of which came first. Instead, we can recognize that the universe may operate through many pathways at the same time, with several processes unfolding in parallel. What we observe is the combined result of many different factors. Astronomers can compare these systems and search for broader patterns, but every galaxy still carries a story of its own. Some dark centers appeared early, while others formed later. Some galaxies began with heavy black hole seeds, while others began with smaller ones. The surrounding matter, the flow of gas, and the background radiation all helped create these differences. This is how Webb is allowing human beings to see the diversity of the early universe, where each galaxy developed according to its own rhythm, while still following the same fundamental laws of physics. The early universe was therefore a diverse and flexible place, where black holes and galaxies did not follow a single path. The appearance, growth, and influence of a black hole depended on the gas, dark matter, radiation, and history of matter within each individual system. With Webb, human beings are gradually beginning to picture this complex but richly varied story of black holes and early galaxies evolving together. A black hole does not emit light, so human beings cannot simply place it on a scale or measure it directly. Its mass does not appear as a visible number or as a surface that can be observed. Instead, scientists rely on the effects the black hole has on surrounding matter, especially gas and light, to estimate its mass. These effects act like clues, allowing us to weigh an invisible object by studying the way it makes nearby material move. Gas around a black hole does not usually fall straight inward the moment gravity begins pulling on it. Instead, it often circles the center, forming orbital paths or a rotating disk. The speed of that rotation depends on the strength of the black hole's gravity. The closer the gas is to the center, the stronger the gravitational pull becomes and the faster the gas moves. By observing these streams of gas with telescopes, scientists can use their speed to reveal the hidden mass inside. One of the most important tools is the spectrum of light. Light emitted by the gas carries traces of both the material's composition and its motion. When gas rotates rapidly around the center, the spectral lines in the light may broaden, shift, or become distorted. By studying these features, astronomers can determine the speed of the gas and then estimate the gravitational force required to keep it moving that way. When this information is combined with the size of the glowing region, the mass of the central object can be estimated. This method is similar to observing a heavy object hidden inside fog. You cannot see the object itself, but you can see particles of dust moving around it. From their motion, you understand that something massive is holding them nearby. A distant black hole works in much the same way. It cannot be seen directly, but the rotating gas, the light released by heated material, and the distribution of matter around it reveal its gravitational pull and mass. Another highly useful tool is gravitational lensing. When a large concentration of mass, such as a galaxy cluster, lies in the foreground, it bends the light arriving from a distant black hole, acting like a natural magnifying glass. This phenomenon enlarges the distant object and makes details that would otherwise be too small easier to observe. Through gravitational lensing, scientists can measure the speed of the gas, the shape of the accretion disk, and signs of energy with greater precision. Seen in this way, measuring the mass of a black hole is a delicate process. There is no direct reading, only many indirect signals. The rotational speed of gas, the radiation being released, the arrangement of surrounding matter, and the magnifying effect of a natural gravitational lens. From these signals, astronomers build models and compare observational data with theoretical predictions to estimate the mass at the center. To picture this more clearly, imagine a system rotating around a hidden central object. Gas and dust circle a black hole, much like water swirling around a stone submerged at the bottom of a stream. You cannot see the stone, but by watching the water, you know that something is influencing the current. The speed and direction of the swirling water reveal the position and influence of the hidden object. In the same way, gas around a black hole reveals the gravity and mass of the unseen center. What makes this method especially valuable is that it can be applied to many black holes, not only one. It allows scientists to measure black holes in distant galaxies, where the light is faint and the objects appear extremely small. As more data is collected, researchers can compare black holes, identify patterns in their growth, study their interactions with surrounding galaxies, and examine their effects on gas and stars. This helps reveal how black holes influence galaxy formation and evolve alongside their environments. The mass estimated from the speed of the gas and the size of the glowing region also provides information about the black hole's development. The more massive the black hole, the stronger its gravity and the faster nearby gas moves. Light produced by the gas reveals its temperature, density, and the amount of energy being released. When all of this data is combined, a more detailed picture of the central mass and its accretion process begins to emerge. Gravitational lensing also helps reveal extremely small details that ordinary telescope observations might miss. It can make the accretion disk, the rotating streams of gas, and the regions dominated by the black hole easier to see. Because of this, black holes, located billions of light years away, can still have their masses estimated with greater confidence. The measurement of distant black holes therefore does not depend on seeing them directly. It depends on their effects on surrounding matter and on the light that matter produces. The speed of the gas, the distribution of material, the strength of the radiation, and the effects of gravitational lensing all provide important clues. Scientists combine this information to estimate the black hole's mass, determine its accretion rate, and understand how it influences its host galaxy. This method also shows why the environment around a black hole matters so much. gas, stars, and dark matter all contribute to the way a black hole attracts material and affects the development of the central region. By analyzing moving gas and emitted light, human beings can measure the hidden central mass without directly observing the black hole itself, much as we can recognize the presence of a heavy object by watching the things around it move. Thanks to these observing techniques, distant black holes in the early universe have become measurable. Each measurement provides another clue about how dark centers grew, how they interacted with gas and stars, and how they influenced the development of the galaxies around them. Through these clues, human beings are gradually learning how the first black holes evolved alongside their host galaxies. When we observe an object at an enormous distance, especially one more than 13 billion light-years away, everything becomes much more difficult. The light received by a telescope is no longer a clear, complete image that can be easily interpreted. It has traveled across an immense distance. Along the way, it may have become weaker, changed in color, blended with other light, or been magnified in an uneven way. For this reason, a major discovery in the distant universe cannot be interpreted too quickly. When scientists detect signs of a very distant black hole, they do not see the black hole itself as they would see an ordinary object. A black hole produces no light of its own. What they observe is light from the gas around it, from nearby stars, or from the central region of its galaxy. These sources may lie so close together that separating them becomes extremely difficult. Some of the light may come from hot gas surrounding the black hole, while another portion may come from stars. Without careful analysis, scientists might assume that the source is bright because of the black hole, even though some of the light is actually being produced by the surrounding stars. Cosmic dust also makes observation more difficult. This dust is not exactly like the dust found inside a room, but it can be understood as extremely small particles of matter drifting through space. When light passes through a region containing a great deal of dust, it may become dimmer or change in color. An object may appear redder not only because it is extremely distant, but also because its light has passed through dust. If this effect is not taken into account, scientists may misjudge the object's distance, brightness, or true nature. Gravitational lensing must also be used carefully. This phenomenon occurs when a massive galaxy cluster in the foreground bends the light from an object behind it, acting like a natural magnifying glass. It can make extremely distant objects easier to observe. But this cosmic magnifying glass does not always enlarge every part of an object equally. Some regions may be magnified more strongly than others. The image may become stretched, distorted, or brighter in certain places. When gravitational lensing is used to study a distant black hole, scientists must therefore determine precisely how the light has been altered. Even measuring the mass of the black hole is not simple. Scientists often study the gas near the center. If the gas is moving rapidly, they may infer that a large mass is hidden there. But gas motion is not always orderly or easy to interpret. The gas may rotate at an angle, become disturbed, be driven outward, or be affected by several sources of energy at once. If researchers rely on only one sign, the result may remain uncertain. The mass of the black hole's host galaxy is also difficult to measure. Before scientists can determine whether a black hole is unusually massive compared with its galaxy, they must first estimate the mass of that galaxy, how many stars it contains, and how much gas is present. But in a very distant galaxy, the light is extremely faint, and the object appears very small. Any estimate of its stellar population includes uncertainty. If the stellar mass is underestimated, the black hole will appear too massive. If the stellar mass is overestimated, the relationship between the black hole and the galaxy will shift in the opposite direction. A major discovery, therefore, cannot depend on a single measurement. One research team may identify a highly significant signal, but more data will still be needed afterward. Scientists need clearer light, deeper observations, and more similar objects for comparison. With only one example, It is difficult to know whether the object is a rare exception or evidence of a broader pattern. Only when more examples are found does the larger picture become more secure. This is why science often moves slowly, especially when dealing with discoveries in the distant universe. Moving slowly does not mean lacking confidence. It means avoiding conclusions that come too soon. A signal may be extremely compelling, but it must still be tested in several ways. The initial interpretation may be correct, but part of the signal may also have been influenced by dust, by the way the light was magnified, or by the blending of starlight with light from the region around the black hole. Scientists do not ask only, "What are we seeing?" They also ask, "Could there be another explanation?" A red object may be an extremely distant galaxy, but it may also be a galaxy containing a great deal of dust. A bright central region may be powered by a black hole accreting gas, but it could also be a region where new stars are forming at an intense rate. Rapidly moving gas may be caused by a black hole, but it may also be influenced by powerful gas flows within the galaxy. A result becomes more reliable only when several different signs point in the same direction. This caution prevents science from being carried away by the excitement of a discovery. A massive black hole in the early universe is extremely important. It could change the way human beings understand the first galaxies, but precisely because it is so important, it must be examined carefully. If the conclusion is correct, it will remain strong after repeated observations. If the evidence is incomplete, later observations will help refine the interpretation. Webb has opened access to an enormous amount of new data, but new data does not automatically become a final answer. It is more like opening additional pages in a very old book about the universe. The writing on each page may be faint. Some sections may be missing, while others may be blurred. Scientists must read each line, compare it with other pages, and only then begin to understand the fuller meaning. That reading cannot be rushed, because misunderstanding even one detail may distort the entire story behind it. This also helps explain why scientists sometimes use words such as may, appears, or is estimated, even when discussing the same discovery. These words are not signs of weakness. They show that researchers are describing the evidence at its true level of certainty. When observing objects at such enormous distances, maintaining a degree of caution is necessary. It allows science to remain honest about what has actually been measured. A major discovery, therefore, does not end when it is announced. Instead, it begins a new process of testing. Other teams may observe the object again. New data may make the result clearer. Improved models may help separate light from the black hole region from the light of surrounding stars. Similar objects may be discovered, revealing whether the phenomenon is rare or common. Through each of these steps, the original finding gradually becomes more reliable. This patience is one of the beautiful parts of science. It does not make the mystery disappear. It allows the mystery to become clearer. Instead of immediately claiming that a black hole certainly formed before its galaxy, science asks more slowly, what does the data actually show? What information is still missing? Are there other possible explanations? Where should the next observations be made? By asking these questions, every eventual answer can rest on a stronger foundation. With extremely distant black holes, discovering them is not the only important task. Understanding them correctly matters just as much. How massive are they? How large are the galaxies around them? How is the gas moving? How have dust and gravitational lensing altered the light? Each smaller question helps prevent a premature conclusion. When these questions are tested carefully, the picture of the early universe becomes more trustworthy. A major discovery must therefore still be examined patiently. This is not because science is indecisive, but because the universe is both extremely distant and deeply complex. The light that reaches us has traveled through an immense journey, carrying many clues but also many features that must be decoded. Caution allows human beings to place each discovery in its proper position, so that the story of the first black holes is not only fascinating, but also closer to the truth. New discoveries about black holes in the early universe do not erase the older story. This is important to understand. When the James Webb Space Telescope observes distant, small, red objects or black holes that appear larger than expected, it does not mean that everything human beings previously understood was wrong. Science rarely changes by completely erasing an old picture and starting again from nothing. More often, it adds new details, fills in missing areas, and makes the larger picture more complete. The familiar story still has value. The first stars may still have produced black hole seeds. A very massive star could reach the end of its life, its core could collapse, and a small black hole could be left behind. That black hole could then continue drawing in gas, gaining more matter, and growing over time. This pathway remains reasonable, necessary, and an important part of how human beings understand the first black holes. Black holes may also continue growing through accretion. Before going further with that term, accretion can simply be understood as the process in which a black hole draws surrounding gas and matter toward itself. That material heats up, begins to glow, and some of it eventually falls deeper inward. Through many periods of accretion, the black hole gains mass. This is not a new idea, and it remains one of the main ways black holes are thought to grow. Mergers also remain part of the story. A merger simply means that two objects combine into one. In the universe, smaller galaxies can collide and join together. If each galaxy contains a black hole at its center, those black holes may gradually move closer and eventually merge into a larger one. This allows a black hole to gain mass without depending only on the gas it consumes. It also helps explain how black holes in mature galaxies can become so enormous after billions of years. But the new discoveries suggest that this familiar story may not be enough on its own. If some black holes were already very massive when the universe was still young, then beginning only with small black holes left by the first stars and allowing them to grow slowly may not explain every case. Some black holes may have begun with heavier seeds. A massive gas cloud may have collapsed directly toward its center instead of first forming stars, creating a heavy black hole from the beginning. Some black holes may have experienced brief periods of much faster than normal accretion. And in a more speculative possibility, certain black holes may have existed from a very early time after the Big Bang. These possibilities do not need to exclude one another. This point should remain clear. The universe does not have to choose one single path for every galaxy. Some black holes may have come from the first stars. Others may have formed through the direct collapse of gas. Some may have grown rapidly during several intense episodes of accretion. Other hypotheses leave open the possibility of primordial black holes that formed during a very early stage of the universe, before the first stars were born. Seen in this way, objects such as QSO1 and GN-z11 can be placed in a more appropriate context. They are not final answers to the entire question, nor do they prove by themselves that black holes always formed before galaxies. Their value lies elsewhere. They show that there are cases in which the familiar model may need to be expanded. A massive black hole inside a young galaxy, or evidence of an active black hole at an extremely early time, provides a clue that encourages scientists to look more closely. The little red dots in Webb's data should be approached in the same way. They should not be identified too quickly as enormous black holes. Some red dots may be dusty galaxies. Others may contain large populations of young stars. Some may contain highly active central regions. But this uncertainty is valuable in itself. It suggests that the early universe contained more kinds of objects, more environmental conditions, and more pathways of development than the original, simpler picture allowed. What the James Webb Space Telescope is doing is not providing one single answer. It is expanding the region that human beings can observe. In the past, we could see only a small part of these extremely distant periods. Many objects were too faint, too small, or too red to study clearly. Webb now allows scientists to look deeper and reach earlier stages. It enables them to measure light, read signs carried by gas, search for evidence of black holes accreting matter, and compare many early galaxies with one another. The older story has therefore become broader. Instead of only one path leading from gas to stars, from stars to small black holes, and then from small black holes to massive ones, there are now several possible branches. Some pathways are slow, others are fast. Some require highly unusual conditions. One galaxy may develop its stellar population first. Another may contain a dark central object that grows more rapidly. One system may gradually reach a balance after a long period of time, while another may begin with a clear difference in timing between the black hole and the surrounding galaxy. This broader view also helps us avoid an overly rigid question. Is the old model right or wrong? In science, that question is often not useful enough. A model may explain many cases correctly, while still needing to be expanded when new observations appear. The older model, in which black holes form from stars and grow through accretion, remains valuable. It is simply no longer the only possible explanation for every massive black hole in the early universe. A deeper question is how far that model needs to be expanded. Do scientists need to include heavy black hole seeds? Must they include periods of exceptionally rapid growth? Should they account for denser gas environments, earlier mergers, or unusual conditions in the first universe? How widely should the possibility of primordial black holes remain open? These questions do not weaken science. They make it more precise. When a scientific story becomes broader, it does not necessarily become more confusing. It simply moves closer to reality. The universe does not have to be simple in order for human beings to understand it. It may contain many pathways, many rhythms of growth, and many exceptions. The work of science is to determine which pathway occurred, under what conditions, and which signs allow one possibility to be distinguished from another. The new findings, therefore, do not destroy the foundations of the older picture. They are more like additional pieces placed onto a map. The map already contains several major routes. Webb is now revealing side roads, unnamed regions, and pathways that appear only under special conditions. When those pieces are placed correctly, the story of the first black holes does not lose its order. It simply becomes larger. What remains after this journey is a more flexible but also more reliable way of seeing the subject. Black holes may come from stars, they may come from collapsing gas, they may grow rapidly during brief periods. Some more distant possibilities still require additional evidence. QSO1, GN-z11, and the little red dots are not the final punctuation marks in this story. They are milestones that show human beings how much richer the early universe was than any single explanation could describe. Rather than asking whether the older model is right or wrong, perhaps the more useful question is this: how must the older story be expanded to include everything Webb is now revealing? Asked in this way, new discoveries do not reduce the value of earlier scientific understanding. They give that understanding greater depth, leave more space for exploration, and provide more reasons to continue looking toward the distant light that is still carrying the story of the universe's beginning. After considering all the signs along the way, perhaps the most important thing is not to choose an answer too quickly. There is no need to declare that black holes always formed before galaxies, nor is there any need to reject the familiar explanation in which stars appeared first and black hole seeds were later created by their deaths. The early universe may not have followed only one sequence. What the new observations suggest is a broader picture. In some places, gas gathered, the first stars were born, massive stars died, and small black holes appeared afterward. Elsewhere, an enormous cloud of gas may have collapsed directly toward its center, creating a massive black hole from the beginning. There may also have been cases in which a black hole grew extremely rapidly during several brief periods, then became quiet before beginning to receive more matter again. And among the possibilities that remain open, some black holes may have existed at a very early time, before stars and galaxies had fully formed. These possibilities do not need to exclude one another. They may all have existed within the early universe. One pathway may explain one group of galaxies, but fail to explain another. In some places, the light of the first stars may have opened the story. In others, gas may have rushed toward the center first. In some systems, the black hole may have arrived only as a later result. In others, a dark central object may have appeared early, while matter gradually gathered around it, began to rotate, cooled, formed stars, and slowly built the shape of a galaxy. The question of whether black holes or galaxies came first should therefore no longer be treated as a simple choice between two answers. It depends on the particular environment of each region in the early universe, whether it contained a great deal of gas or very little, whether that gas cooled quickly or slowly, whether the original central object was large or small, and whether the black hole was active enough to alter the surrounding material. When understood within these conditions, the story becomes more flexible, but also more accurate. The universe did not need to follow only one sequence. Each of the first galaxies may have had its own beginning. QSO1, GN-z11, and the little red dots in Webb's data are not final answers. They do not exist to prove that every galaxy began with a black hole. They are more like small markings on an ancient map, suggesting that the order of formation in those distant regions may have been more varied. A black hole that appears too massive for its young galaxy. A central object accreting matter when the universe was still very young. A faint red point whose light is difficult to explain. Each individual sign still requires careful testing, but when they are considered together, they expand the picture of the universe's earliest years. What is valuable is that science does not rush to turn surprises into conclusions. When astronomers see a faint spectral line, they examine it again with care. When they estimate a mass, they check the measurement repeatedly. When they observe a red point of light, they analyze it closely to determine whether the source is stars, dust, or hot gas surrounding a black hole. This slow examination of every detail does not make the story less compelling. It makes the results more trustworthy and provides a stronger foundation for the next steps in understanding the universe. The mystery does not disappear. It simply becomes clearer. In the past, human beings may have asked broadly where the first black holes came from. That question now has more shape. We know to examine gas moving around the center. We know that light can carry traces of motion. We know that a small galaxy may still contain an extremely massive central object. We know that a black hole does not simply remain motionless inside a galaxy, but may heat gas, drive it outward, hold it nearby, or change the rhythm of star formation around it. Science does not make the universe less strange. It brings that strangeness closer through data. Something that once existed only as a vast question in the imagination can now be connected to specific signals. A tiny bright region, a rotating stream of gas, a shifted line of light, or a mass estimated from the motion of something that cannot be seen directly. Human beings do not merely remain amazed. They begin to understand why they are amazed. Perhaps this is the deepest value of the journey. It is not only a story about black holes. It reminds us that the patterns we use to understand the world are sometimes only the first, simplified versions. When better data appears, those patterns do not always need to be discarded. They can be expanded. They gain new branches, new exceptions, and new areas of uncertainty. Those unknown regions are part of what keeps science alive. The early universe may have been more complex than a single, straight sequence. It may not always have been a story in which gas formed stars, stars formed black holes, and black holes then grew inside galaxies. Sometimes stars may have come first. Sometimes gas may have collapsed first. Sometimes the black hole may have grown faster than the galaxy around it. And perhaps, in a few extremely distant places, darkness was already present at the center, before the light of many stars had time to fill the surrounding home. This does not make the story colder or more remote. Instead, it gives the universe greater depth. A tiny red point is no longer only a faint mark in a set of data. It may be a trace of a period when everything was still finding a way to form. A stream of gas circling an invisible center may remind us that even the darkest object can leave signs behind. A black hole at an enormous distance can lead human beings back to a question that once seemed simple. What came first? The answer is still not completely within our reach. And perhaps that is the most fitting way to bring this story toward its end, not with a sweeping declaration, but with a slower understanding that the universe was never required to grow according to one single order. The first galaxies may have begun through many pathways. The first black holes may have had many origins. And the new data from Webb is allowing human beings to see that diversity a little more clearly with every observation. At the end of this journey, what remains is not a sealed answer. What remains is a broader way of seeing the beginning of the universe. Light, gas, stars, and black holes may not have appeared in one fixed order. In a few very distant places, a dark central object may have formed early enough to hold surrounding matter and help a galaxy slowly take shape. The new data does not make the mystery disappear. It makes that mystery clearer, deeper, and more worthy of continued attention, guided by all the patience that science can offer.